The following was presented at the 10th Dry Dock Conference. Registration is now open for the 11th Dry Dock Conference. Visit drydockconference.com for more information. The 2025 Dry Dock Conference will take place on the 4th and 5th of June, 2025 in Providence, Rhode Island, USA. This is the 11th International Dry Dock Conference and Advanced Training Forum, hosted by DM Consulting. Registration is now open for in-person and online attendance. Visit our website to register and register early for a discounted rate.
Tim Greeson is our next speaker. He's an independent naval architect, structural engineer. He's got a PE, 10 plus years dry docking and dry dock experience. He's going to talk about the dry docking fix and the lifting of the Texas. Tim,
right.
your turn.
Sweet. Thank you, Joe. Talk to y'all about a cool new dry dock that's new to us. GC 35,000, GC standing for Gulf Copper. They're a shipyard based in Texas. They have a yard in Galveston, a yard in Port Arthur, a yard in Corpus Christi, and then they have other ventures in places here in Norfolk. They've worked in Portland, Guam, several other places before. So they GC 35,000 is the nominal capacity of 35,000 tons. And I'm going to talk to you about a great ship today. That's the Battleship Texas, named after the greatest state in the Union, where we're known for being humble and quiet. So this is the stuff we're going to talk about. So there you go. The Battleship Texas, this is it up, so we're successful. So I told Joe I may or may not attend. It depends on how it goes. So I'm here. It went well. The Battleship is neat. I'm not going to give you the full Wikipedia of it. You can go check it out. But it's got a lot of firsts for American battleships. It was the first battleship to launch an aircraft carrier. It was the first battleship to receive anti-aircraft guns. It's the last remaining floating World War I dreadnought. It's also the last remaining capital ship that's worked in World War I and World War II. It's got a lot of distinctions. It was the first battleship to open up shore bombardment on D-Day. It fought North Africa, South France, Normandy, Iwo Jima, and Guadalcanal. So great history. 1948-ish, it was given to the state of Texas, the first namesake vessel ever donated to a state. It's been a museum ever since at the San Jacinto Battleground, where Texas won its independence from Mexico. So it's a big part of the state identity. If you follow the maritime industry at all, it's been all over YouTube, LinkedIn, everything. Unfortunately though, although it's a great ship, was not taken care of very well. And it's been 34 years since it's been dry docked. So it's quite a while. It's had a lot of temporary repairs, a lot of concrete cofferdams, a lot of foam added to it. And it's time. It needed to come out of the water. A few years ago, the management of the ship was transferred from Texas Parks and Wildlife over to a third-party nonprofit organization called Battleship Texas Foundation. They've taken over and really trying to get this thing back up and repaired. So we started looking and being the Battleship Texas, funded by Texas, we didn't want to send the ship too far out of state, if at all. We'd rather work on it and keep our taxpayer dollars in the state. And Amfels was the only place in town or in the state that had a dry dock capable. For whatever reason, they weren't able to do the work. We looked at going to Alabama and combined with going to Brownsville or going to Alabama. We weren't sure the ship could actually take it. She'd had multiple structural analyses done. We just weren't sure it was going to go open ocean. So at the same time, dry dock number 2 or 4, I don't remember, but one of the dry docks in Grand Bahama Shipyard broke, longitudinally and transversely. So half of that dry dock was identified as being sufficient to lift the Texas, so the management, Battleship Texas Foundation hired a company, an engineering company, to kind of look into that. They determined it was useful. They brought the project to Gulf Copper, and Gulf Copper said, yes, let's take a look at this. We're interested in it, and all parties kind of came together and ended up buying the project and doing the project. So Gulf Copper purchased the less damaged half of the floating dry dock, did the restoration, and then did the lift of the Texas. So that's what we're going to talk about today. Joe said I only have 6 hours to do this, so I took out all the 3D vector calculus. I know y'all are excited about that, except Primo. I see the disappointment in his eyes. But so this is how it was when we got there. You can see it had already been, the salvage company had already cut it in half, and the other half of the dock, unfortunately, part of it had already been scrapped and turned it into a barge, okay? This is the damage that we saw. So it was damaged longitudinally and transversely almost at the midpoint. So the transverse damage is where it was cut, and the longitudinal damage was still remaining in place. And there's kind of where you can see there's a set of bulkheads here. It doesn't have a void. It has a centerline bulkhead. It has structural bulkheads at the 44-foot off center line, which are partially tight. They're tied up to 10 feet with sluice gates. But structurally, they go all the way to the deck. And it was damaged just outside of that bulkhead. So another thing, I'm not going to discuss the damage. I've been told 5 different stories before yesterday, and last night I got a 6th one. So I don't really know how it was damaged. I just know that it was. This is what I saw. So there's a good photo of it. You can see it was cut right here, portions of the apron from the other side. You can see here's the longitudinal piece, and then there's the other half of the dock that was turned into a floating deck barge. So you can see here the salvage contractor had placed some temporary beams on it to stop it from compressing anymore. They were only compression beams. The end fittings were brackets with some wood in them, and they were held in compression by differential loading the tanks. The salvage contractor had gone in and added some more subdivision in a few places so they could control the loading a little bit more. Here's a closer up view of the damage down the dock on the pontoon deck. This one's a little bit harder to see, but it's a transverse bulkhead, and you can see the damage going all the way to the bottom. But importantly, the bottom shell was not damaged, so the bottom was still continuous. So that's kind of where I took over. So there's not, how do we start with this? Well, here was our engineering design basis, kind of what we decided to do. Here's some of our reference guides and things we use to go through the restoring the dry dock. Task number 1 was to straighten it back out, because unfortunately if we had failed or if it hadn't worked out, none of the rest of it would have mattered. So I say we, so another life lesson, there is nothing you can't accomplish if you're willing to take credit for other people's thoughts, okay? So a guy named Jonathan Hale, actually, he's a vice president at Gulf Copper, came up with quite a few of these ideas. I was just the guy that did the math and did the quantification of the scalings, if you will. So the idea was we would start by making sure that we had enough of these compression beams. They had enough for salvage, but not enough for comfort, if you will. And in addition to that, we had to have a way, as we were straightening it, we had to lock them in. So we had to convert them from compression only to tension and compression. Okay? So here's those beams beforehand with the brackets, and they're bolted originally. And we converted them. We added welds, and then it's kind of hard to see, but we added this piece here. And the idea was we would have shims on either side as we straighten the dock out. Do I have? Okay, I did not. So here's more of the damage. You can see the beams going down there, additional beams added. All right. So the way we straightened it, once we had the beams in place, we had locking beams and we had kind of movable beams. So as we would go, we made a pie cut in the damaged bulkhead. so that it was pinned, if you will, once our restricting beams were in place. Then we set up an optical transit. Where's that laser at? Here we go. So we set up an optical transit with targets relative to the bottom. Because again, the bottom's undamaged, just needs to be straightened out. And then we basically, after we had made that cut, we started pumping using differential water levels to straighten out the dock. And we use that optical transit to shoot across and know how far off are we. And you can see, as we're going, we're taking notes. So this is the optical transit's on the other side. This is the target. This is where we started. This is going along. You can see the dates and the times. It was about 36 inches we had to move. And this is us in the final configuration. That's the best shot we could get through the transit. But basically, it ended up working out. As the deck opened up, we would take shims from the tension side of those locking beams and move them to the compression side of the locking beams. So that if for some reason we had a wind kick up or we had something let loose and the dock just wanted to completely undo, it had a limit where it can only travel an inch or two. All right. So once it was straight, the beams were locked in by welding them. We removed the shims, welded them down, locked them in, and we started doing repairs. Cut out old sections, put in new sections. One of the benefits of this project, the portion that had been scrapped was still sitting right there at the city dock. So Jonathan was able to walk around and find pieces that used to be a bulkhead, that used to be wing walls, and other used to be pontoon deck. The bottom deck, the bottom and the pontoon deck had the same scantlings and the same spacing. So we were able to use some of the old bottom for new pontoon deck as well. So we were able to reuse a lot of the steel that was already on the ground. We didn't have to fabricate a whole lot of new stuff other than trying to work it in. There's putting in a deck section. We also did a set of gaugings on this dock before they bought it and found that the dock was in fairly good shape. The pontoon deck is a little corroded. I know you guys don't know what that is because it's very rare for a pontoon deck on a floating dry dock to be damaged, but everything else was very good. Here we are repairing multiple sections at once. And the transom. So the frame 41 used to be a regular ring frame and obviously became our new transom. So we had a little work to do with that. It was a little bit unusual, mostly on the fabrication side. The engineering is the same, but the molded side of a bulkhead or a frame is typically the aft side except for the aft transom. And that was the case in this dry dock. And the problem is we needed to plate in these rings in order to have a watertight transom, because that's what you want. So we placed in we did the calculations to know what the shell thicknesses needed to be. Then we did the calculations to know what the new stiffeners needed to be. But the challenge was, because it's not the molded side of the plate, this dry dock was built with a whole lot of different plating thicknesses in each of those frames. You had 12 millimeter plate over here, you had 18 over here, you had 24 up in some places. So it was very strange. So to get those stiffeners to work right, we had to make very long, tiny cuts. You know, just grinding, shaving them down, and they did it. It worked out. But that was a challenge for the fabricators. You know, they'd much rather take an inch off than an eighth of an inch off or a quarter inch off. It's hard. It's kind of harder to do. But we were successful. We did it. The outside stiffeners in this picture, you can see, we ended up leaving them. But this transom has been stiffened completely on the inside, where these stiffeners are just there for grins, you know, so we can enjoy the picture. They aren't doing any structural work. Well, they are doing structural work at the present, but they're not accounted for in the structural calculations. So the next challenge we had, as I mentioned, is the pontoon deck. And this is a slide that Jonathan came up with that I analyzed with him. And the question is, what are the renewable thicknesses? So I did the docking calculations to know what was our pumping plan and what was going to be our hydrostatic pressure on the dock, and found the renewal thicknesses that way, rather than using a when you convert docks, which I've done several, you can't take for granted that the original design, or let me back up. Normally, your allowable diminution is a percentage of the original plate thickness. So let's say I do a calculation and find that the plate thickness only needs to be a 1/2 inch. Well, if I'm designing a dry dock, if the budget will allow, we're going to put in a 3/4 inch or a 1 inch so that you have plenty of room to corrode. Well, it's not fair to the dry dock to then take away and say you're only allowed to diminute, to waste away 25% when you've already got, 2 to 3 times what you need in there. So we did some analysis to find what would be the actual minimum calculation per ABS rules based on the docking we're doing, and then we took a 25% diminution off of that to set our renewal thickness. And we found out was around, believe it or not, around 50% of the original design. That said, all these areas in orange and red, especially in through here, are even below that. So where we could, we inserted as much plate as we could. You saw the deck sections where the damage was. We took a lot of those sections from the Bahamas as well and inserted. But the schedule, and the Battleship Texas is being funded through the state legislature, so there's timing involved with that as well. So the schedule is very critical, which I know is unusual. Normally, your ship project schedule isn't a big deal, but it was in this one, okay? So in order to accomplish that, we had to do some structural doubling, and that was a unique challenge as well. Structural doubling is not normally a good thing, and it's actually not really addressed in many codes other than to say it's a temporary repair for when you have to do it. There is a committee or a group called the Ship Structural Committee. Some of y'all know of them. And they actually have published guidelines for doubler plates to be used as structural elements. And so in order to accomplish the schedule, that's what we ended up designing to add thickness to a lot of our dock. This would solve our hydrostatic issue, our hydrostatic pressure issue, but we also had some strength issues, which I'll get to in just a second. But this shows you the design. So we add these doubler plates, and we weld the perimeter of the doubler plate as well as in these slot welds. And the Ship Structural Committee gives you slot welding schedules that you can use that account for, that basically turn that doubler into an effective part of the plate. There's limitations and other things like that. So you can't just go crazy, and it's not a permanent solution. But this docking wasn't for the Navy or the Coast Guard. It was, and the ship is planned to be up for a year, so we've got a whole year to fix it between our next docking, which is the plan. So speaking of structural, we did a transverse structural check because it had failed transversely, and now we're doubling the plates with these doublers with structural issues. So we developed the shear and moment diagrams, and the places highlighted in red here are the same places that correspond to these locations in the transverse. And we modeled, we kind of looked at the worst case scenario, and you see, as is expected, although it's higher, you do have high shears, but that's not really necessarily carried by the deck plating. It's more in the transverse framing. And then your moment diagram, again, you're not dealing with the highest moment area, okay? So structurally, we thought that was a best commercial solution, and it worked. It worked great. Flipping over to stability, I got to give a big thank you. Besides to Gulf Copper, I also have to give a big thank you to Orca 3D. I don't know if y'all use them. I'm a one-man shop. I do all my work in Rhino. I do analysis, CAD, modeling, everything. Orca 3D is based in Rhino. It's an analysis tool. They used to be certified by the Coast Guard for stability. They were taken off a list because they didn't have free surface effects, so I'm actually beta testing with them their new version of their software that will do free surface effects, and they gave me a beta testing model to help them test it, but also to do this project. So I constructed a model, did the calculations, found the max displacement, the max kg of the ship, and anyway, so that I'll come more to the Texas specific stuff in just a second. Another thing that came up is tonnage. And you know, some people ask me, some people who aren't familiar with naval architecture, they always ask me, why do you have short tons, long tons, metric tons, gross tons, net tons? And I tell them, well, first, gross tons and net tons are not a weight. And then they, you know, they get more mad. Well, why do you guys do that? I say, well, listen, if it was easy, you wouldn't pay me, right? So leave them confused a little bit and just know that it works, and they need to keep sending you the checks, right? So, but we had to do a tonnage assessment because we had to get a certificate of documentation. The old doc had a certificate of documentation. I don't know where it was issued out of, but it, you know, effectively a title. Well, now we've taken that old doc and cut it in half. The original certificate of documentation was updated, but remained with the other half because that barge was completed first. And there was a period of time where they didn't know if they were going to sell this dock or if they were going to scrap it or what they were going to do. So in order to import it into the United States, it has to, or to go on an international voyage at all, it has to have some kind of registry and some kind of documentation. To get a certificate of documentation, you have to have a tonnage assessment. So I did the tonnage assessment. We sent this off to ABS to do the actual tonnage certificate, which they did, and got it taken care of. So international tonnage is very easy. Domestic tonnage is complicated black box, so that we continue to have job security, I guess, is the only reason we have that. But towing, we had to tow it from the Bahamas to Galveston. We basically used the Navy towing manual. Where published values were available, we used them. There's a lot, if you look in the Navy towing manual, there's a lot of recommended drag loads and wind loads. So rather than using the tables, because the dry dock isn't in those tables, or at least this dry dock wasn't, we did calculations that then we plugged into the formulas in the Navy towing manual to size all of the wire ropes and everything else. Here's the some of the towing configurations. Your emergency tow line. We used ABS equipment number to size the anchor and the number of shots of anchor chain we had to have, all that kind of stuff. This is it, ready to go. We took those same deck beams that we used and tied the aprons on. The aprons were pinned on originally so they could be removed if they had to be. To my knowledge, they were never removed, but we did have a few that were removed up here that are stored on the deck, and then we used these beams, welded them down, secured the apron from bending, towed it over. Not ideal conditions, but not bad. Always fighting that loop current in the Gulf. Winds were good. Winds actually, this is just one of the shots, but winds actually picked up and pushed her up a little bit. And there she is coming out, getting ready to be towed. That's about 1.5 years worth of work, at least, right there. Towed well and arrived in Galveston. And last thing, I kind of kept this presentation to the aspects that I did personally, but since there's a little more involvement, the machinery, I just wanted to show you all the pumps coming out. Steve was just telling a story. Steve is the CEO of Gulf Copper back there. He was telling us a story about some of the motors. We had some issues with motors, pulled them off, found out we thought they were going to be able to be rebuilt, went to actually rebuild them, and they were not able to be rebuilt. So that was one of our last procurement schedule critical items. Ended up having to buy motors in China, air freight them to Houston, and of course, everything you get from China is always perfect. It fits 100%. So that was fantastic. So we'll shift over and talk about the actual blocking and docking of the Texas. So the Texas is a unique ship. I've never seen this. I'm sure some of y'all have. It has what they call docking keels, which are effectively skegs, which if you were to ever heavy lift it, it makes it really easy. It's like docking a flat bottom barge. So it's very strange, but it's good for us. So we always have this question of, if I'm going to put blocks, do I match the vessel frame so I don't damage the vessel, or do I match my dry dock frame so I don't damage my dry dock? Well, in this case, because it has these longitudinal docking keels, those effectively act as longitudinal structures, which then can intersect our transverse frames, and it made it very easy. Transverse frame spacing is typically 8 foot, 12 foot, 16 foot. So, of course, this dock has an 11-foot transverse frame spacing, which matches nothing, okay? So we always have a problem, but we always know we got it. You know, you guys are surprised. We know it's going to be a problem, okay? So here's the blocking plan. It's a little bit closer. We did with the blocks are completely new. I have a slide coming up, I think, on those. And the docking keels, you can see here, are flat. This is an exploded view, but this one's actually flat as well. And then the outermost docking keel, the auxiliary side blocks, are actually 3 inches above, but again, they're flat, just 3 inches above. Here's a view of the docking keels on historic ships. Their drawings are often very hard to read. Crash your computer, because you know the old school naval architects, they didn't have a standard size. They would just draw and draw and draw and draw until they were done. So we have, you know, some of these drawings are feet and feet and feet long. But we scanned them the best we could. Here's the example of these docking keels. So you have the main keel right here. You have the forward auxiliary keel directly under the front 2 gun turrets. You have the main side keel, which is actually most of the ship, and it's hard to see, but it curves in just slightly, a few inches here. And then you have the auxiliary side blocks, which again curve in slightly. So when we were starting to do these, and they asked me, "Hey, can you design the blocks?" I said, "Why? Let's just use the Navy standard blocks." I called Joe. Joe sent me the Navy standard block, and they said, "Okay, that's great, but we want it a little bigger and a little different because that's what we want." So that's what they got. So it's 3 foot by 5 foot, but you can see the details are based very similar on Navy. It's basically a Navy towing block that we've stretched, not towing block, a Navy dry docking block. Here's an exploded view of the block. So we had our main block here at 3 feet. We built a sandbox because every single one of these is going to have to be fleeted and painted and repaired underneath. And then we have some shims as needed because our new dry dock is close to straight. Okay, it's pretty close. It needs a little help every once in a while. And then we have a set of hardwood on top. Where's the softwood? Well, we decided to eliminate the softwood for several reasons. One is on the bottom of these docking keels, they have teak. I didn't get a detail of it, but they have a really thick teak. Teak is normally a hardwood, but when you submerge it in ocean salt water for 34 years in the Gulf Coast, where we have tons and tons of growth in barnacles, it becomes like balsa wood. So it had a lot in there, it had already there. Secondly, our loads were exceeding, I forget it in PSI, I think in long tons per square foot. So the softwood is designed typically to 20 long tons per square foot. We were right in that 21, 22 long tons per square foot on our max loaded blocks. So rather than we wanted the softwood to crush, but we didn't want it to fail. And because we didn't know the condition of the teak and we didn't know a lot of other things, we said, you know what, we're just going to dock it on the hardwood, and if there's a problem, well, the ship's coming in to get fixed anyways, right? And it's going to be here for a year, and we have a ton of blocks. We have a ton of longitudinal strength here. So if one or two of these blocks don't work out because the wood there is bad or whatever, it's still going to be fine. And that turned out to be 100% right. It was great. It was perfect. So that's the block, though. So once we fleet the blocks, they're going to wedge the blocks back up. Normal wedging is done with a sledgehammer, and you're just kind of guessing at how much force you're putting back into it. So Gulf Copper came up with this idea to build a hydraulic block wedge machine. And again, although they came up with it, I'm going to take credit for it. So I added, they came to me with a design, and it was very heavy, but it worked. So they said, hey, Tim, can you make this lighter and more man-portable? So I took their idea, refined it for them, and this is the result. We did some load testing and averaged them together. It actually worked. I was surprised how consistent the curve was during our load testing. I was expecting that we tested how much pressure we need to apply on the hydraulic blocks to force the wedges together and what was the resulting vertical load. And I was expecting it to vary based on which blocks, how rough the wedges were, and it really didn't seem to. It was much more about the angle, which if you study physics makes sense. But so this is the curve we came up with. Here's the cylinder load, and then they have a certain one that they prefer to use. So I gave them this so they can use a generic load pack, and then if they use their particular load pack, this is exactly what it reads. So, we kind of define a critical docking at Gulf Copper of being 75% of the kg or displacement. And we were a little more than 75%. We were right there on the edge. So we did our, something just fell. We did our stability checks, and then I checked them again, and then I checked them again because we were right there on the edge. I mentioned, by the way, this has partial bulkheads at 44 feet off center line. They're supposed to be tight to the 10-foot level, and they use sluice gates to dewater those areas. The sluice gates either were not operational and they weren't put back into operation. They weren't removed, but they were tied open. So this docking could have greatly benefited from those, but it was safe to accomplish without them. And although there's no, when you're doing the GMT calculations, there's no time in that equation. But in reality, those bulkheads are there with a small pipe in them, right? A small hole. So your instantaneous free surface effects are cut way down compared to what we were actually calculating. So here's the max, here's the minimum GM. Here's our docking evolution. And you can see we get very, very close. Again, I calculated in the spreadsheet, verified with the Orca 3D, although it's beta testing, so we didn't take that 100%. We wanted them to match up. And then here's the hydrostatic pressure through the docking. And this is just a function of the spreadsheet. It's a smooth curve in here in reality. So, and here's our pumping plan. One thing I didn't mention, so we cut off a part of the wing wall. So that means our center of gravity is at a certain point. Our center of flotation changes from one side of the center of buoyancy to the other, which means we have our pumping plan that has to cross itself as we go. So it's a little bit unique challenge, but we were up to it. So it worked out. It's a cool project, and right now they're repairing the ship as we speak. And so anyway, I want to say thank you to these guys, Gulf Copper again. They're one of my main customers. I'm their naval architect, Orca 3D, and then Valcor are the guys that have been retained by the state of Texas to manage this project for them, the Battleship Texas side of it. So with that, are there any questions? I went through that pretty fast, but man, I told you I'd be good, Joe. I told you I was going to answer them all. No questions at all. So, all right. Next.
For more information on this topic and others like it, please see our technical papers. Visit drydocktraining.com/technical-papers or contact DM Consulting at drydocktraining.com/contact-us. Registration is now open for the 11th Dry Dock Conference. Visit drydockconference.com. Thank you for watching.